Thank you. Um, I would like to start by thanking the organizers, which is represented by you, for this invitation to China. It is my second time in China, and it's been a really wonderful experience. So this talk is about joint work with Peter Clarkson. Some of it, the initial work was just with Peter Clarkson, and then later on, it was with Anna Loureiro as well. So they're both from the University of Kent. And I will start by considering introducing you to orthogonal polynomials, which I don't really need in my talk, but they are very closely connected to what I'm doing, and the weights are related to orthogonal polynomials. So I'll start by looking at some classical orthogonality weights, such as the Hermite and the Freud weight. And then I'll look at generalized Freud weights, which have this algebraic term x to the rho. You'll see the Hermite weight is e to the minus x squared. And then for the Freud weight, we increase the power to have even powers. All of these weights will be even. And, but we add the algebraic term as Freud did in order to simplify the calculations. And then we'll do a small perturbation on this exponential power. So we'll add a time-dependent quadratic factor, and that we do for general M, but I'll look at some special cases where M is 3, because we can talk a little bit more about the asymptotics of the recurrence coefficients in that case. And then finally, I will look at a weight where we have still an even power potential here with a quartic term added compared to that, but the algebraic term removed. And we will see that in this case, the behavior actually becomes quite interesting for the recurrence coefficients, but we can't analytically say as much as what we can for the previous cases. So historically, looking at this symmetric sextic Freud work, weight is related to work done in the context of dispersive hydrodynamics in the 90s. And the picture that I have here is the behavior of the recurrence coefficients as it was studied by various authors, and this picture comes from Yerkevitz in 1992, and they describe the behavior here in this transition region of the beta ends as they jump around as chaotic, or Yerkevitz said chaotic pseudo-oscillatory, but his pictures didn't show the oscillatory behavior, and we will try and improve on that. So to start with a quick introduction of orthogonal polynomials, it was Murphy in 1835 who first defined orthogonal function. But 20 years later, Chebyshev was the one who realized their importance, and he was motivated by the analogy of orthogonal functions with Fourier series. Also, he was interested in the perspective from continued fractions and approximation theory. So the easiest way I can introduce you to orthogonal polynomials is by looking at Chebyshev polynomials. And to do that, I'm going right back to a very simple integral. So we're looking at the integral of cos m theta times cos n theta, theta varying from 0 to pi. And this is very well known that this integral is equal to 0 when m is not equal to n, but it's equal to pi over 2 when m and n are non-zero. So note the special case here. When m equals n equals 0, that I'm not mentioning here, then the integrand will be 1, not pi over 2. The integrand will be 1, and the integral will be equal to pi. So in this integral, if we now make the substitution x equal to cos theta, then dx becomes minus sine theta d theta, or we can rewrite that like this. And then when we look at the bounds of the integration, when theta equals 0, x equals 1, and when theta equals pi, x equals -1. And, but we have a negative over here, so the integral can be written in this form. Where now we have a weight function here, which is 1 over the square root of 1 minus x squared. And I've introduced the notation Tn equal to cos n theta, and we have this same integral here. And these are Chebyshev polynomials of the first kind. And we can talk about the Chebyshev polynomials of the first kind being orthogonal because they satisfy this integral condition. That the integral is always 0 when the degree of the polynomials is not the same, and a constant, a positive constant, when the degree is the same but not 0. So then we say they are orthogonal on -1, 1 with respect to this weight which we need to make the integrals behave correctly. So that immediately leads us to the general definition of orthogonal polynomials. So if I have a sequence of monic orthogonal polynomials of degree n in x with respect to the positive weight, then it means that this integral is 0 when n is not equal to n and a positive constant when n equals n. I'm defining it here in the simplest way. Of course, one can define it much more generally in terms of a measure instead of a positive weight. This is the absolutely continuous case. The most important property, so orthogonal polynomials are interesting because they have very, very interesting properties. And the most fundamental property is that if you have a positive weight function, you can define a sequence of orthogonal polynomials, and they always satisfy a 3-term recurrence relation of this kind. And we have the expression of the recurrence coefficients in terms of these two integrals. And this simplifies slightly in the cases I'm looking at where my weight function is symmetric. So if the weight function is symmetric, then we immediately see that this integrand is an odd function so that alpha n becomes 0 because it's over a symmetric interval. And then alpha n, the recurrence coefficient, disappears, and we have a simplified 3-term recurrence relation. In this talk, I'm going to be giving the weights and then trying to find out more about the 3-term recurrence relation. One can also, that's called the direct problem in orthogonal polynomials. One can also work in the other direction. In other words, there is a theorem that says when we have the existence of a 3-term recurrence relation like this, then there exists a measure according to which we have orthogonal polynomials. The trick with working with the inverse problems like that, starting with the 3-term recurrence, is that we don't always know, we almost never know what exactly the measure or the weight looks like. So the classical cases we do, the non-classical cases we don't. But so I'm going to be working from a weight, finding information about the 3-term recurrence, and now I'm going to explain to you how I get from the integral relation to finding more information about, I only have one recurrence coefficient, beta n, because of my symmetric weights. So in the 3-term recurrence, the moments of the weight can be, so the coefficient beta n can be expressed in terms of the moments of the weight, and that is through what is known as Hankel determinants, which is this determinant over here. So I'm going to just call it the determinant of moments. And specifically, what we know is that beta n is equal to the n plus 1 Hankel determinant times n minus 1 divided by delta n squared. And the other thing that we notice is the moment I'm talking about symmetric weights, then all of the odd moments will vanish. If you look here again, so this is the symmetric weight, then the integrand is an odd function over a symmetric interval, and so the mu k's vanish whenever k is odd. And that gives us a lot of simplification. So just to recap, what I'm trying to do is I'm giving you a weight, and then we are interested in finding out more about the moments, which we have an integral expression for, the Hankel determinants, which is just the determinant of the moments, and then finally the recurrence coefficients, which can be written in terms of the Hankel determinants and in terms of the moments, the matrices of moments. So let me just start with a really simple classical weight. So this is the exponential weight, the Hermite weight. And so the Hermite polynomials were orthogonal with respect to that weight. And in this case, we can explicitly calculate the even moments. They're given by this expression, and the odd moments, of course, are 0. And we get a closed form expression for the delta n's, the Hankel determinants. It looks like this. And therefore, we can solve for beta n very simply as this ratio of Hankel determinants, and it's n over 2. Which gives us the 3-term recurrence relation for the Hermite polynomials. This is just a renormalized Hermite polynomial so that the relation looks as simple as possible. Hermite, interestingly enough, I just wanted to make one comment about him. So he is most well known for his work on the theory of functions, including the elliptic function, which he then used to solve the quintic equation. He was a French mathematician, and what I find really interesting about him is that he proved himself a very creative mathematician already at a very young age, at the age of 20. But he had difficulty in passing his formal examinations. And so that forced him to spend 5 years that he devoted, which would have been his most productive years, but he devoted those to finishing his undergraduate degree. So for those of us that are not, he's a genius, but he still struggled with formal examinations, so he didn't do everything at a very young age. So next I'm going to look at the Freud weights, which also are very classical and have been studied a lot, starting with Freud. So the power here is even, and there's an interesting result or comment in the Digital Library of Mathematical Functions, which says that if you look at orthogonal polynomials with respect to Freud weights, it's something like this, where Q is a real, even, non-negative, and continuously differentiable function. And then of special interest are these cases, which is what I had on my previous slides. And then I want to show you this. So it says no explicit expressions for the corresponding orthogonal polynomials are available. So that means that from the moments, it was not straightforward to get the Hankel determinants and the recurrence coefficients. There's no closed form expression for the recurrence coefficients, and so we don't know exactly what the polynomials look like. But there are asymptotic results, and I'll show you those. So let's look at exactly what Freud considered. So he looked at, he added the algebraic term, and you'll see in my talk why this algebraic term actually has a dampening effect on what happens. So in a certain sense, although you're adding something, it simplifies the situation. But these satisfy the 3-term recurrence relation, and now we're trying to figure out what this beta n looks like. And there's no closed form expression. But what Freud did in 1976 is to show that for m equal to 1, which is the Hermite weight, you can express the, so it's Hermite when lambda is minus a half, but he's gone a little bit more general. So we know what we know about the Hermite polynomials for that case. But in this case, he gave this expression for the beta n's. And you'll see this interesting variation between when n is even and odd, which carries throughout for this case. When m is 2, he showed this nonlinear first order equation. And when this is a special case of discrete Painlevé 1. And then when m is 3, he got this nonlinear fourth order discrete equation. And this is a special case of the second member of the discrete Painlevé 1 hierarchy. All right, so this is what was known. And just to put it in the context of what else was known, so these kind of weights, the Freud weight and all the ones I'm going to be looking at from now on, are not classical orthogonality weights. Those would be like the Hermite weight, or for Chebyshev polynomials, or for Laguerre or Jacobi, etc. For classical orthogonal polynomials, we know that they satisfy, the weights satisfy a Pearson equation like this, where this coefficient in the differential equation is a monic polynomial of at most degree 2, and tau is a polynomial with exactly degree 1. So you can characterize classical orthogonal polynomials this way. But for semi-classical polynomials, or orthogonal polynomials, you're moving away from the classical cases. Your weights are getting slightly more complex, but not completely far away. So, because then the problem becomes intractable. But you can characterize them that they will either have this of degree greater than 2, that coefficient, or this one will not be 1. And so the relationship between semi-classical orthogonal polynomials and integral equations, which is what these Pan-Lavey equations are, was studied in 1939 already by Shohad. And he just introduced semi-classical orthogonal polynomials as natural generalizations of the classical ones. And Moroni then provided a unified theory for semi-classical orthogonal polynomials. Right, so I'm now going on to the next weight. So this is no longer the classical order, a higher order Freud weights. It's generalized in the sense that we've added a perturbation term like this plus tx squared. And I've still got the algebraic term, and I'm looking for m2, 3, etc. Now this weight is still symmetric, so the properties up to now hold, and it satisfies the Pearson equation with sigma x equal to x, so that's of degree less than 2, but tau is quadratic, which is not classical. Because remember, quadratic is this greater than 2 or this not of degree 1. And so we have a semi-classical weight. Oh, of course, you're right. So this is not, I'm not just looking at that, but the degree is much higher. Right, but it's not 1. That's the point. So for any m, I'm sitting with a semi-classical weight. And there was a series of papers where we studied these. So actually, I'm talking now more about the results in this, and then I'll go back to the results in this paper to look at the asymptotics. I'm just going to go fairly quickly here, but just to show you where we are going to simplify the expression for the recurrence coefficients, just using the properties of the weights. So for symmetric weights, we have the odd moments vanishing. So this delta 2n can be written as a product of simpler matrices where we've removed all the zeros. And so because beta n is defined like this, we can now write the even recurrence coefficients in terms of these simplified matrices and the odd ones as well. But we're going to use another property of these weights to simplify them even further. So this can be done not just for the weight that I'm introducing, but for any weight of this form, where this is a symmetric positive weight on the real line for which all the weight moments exist. We're multiplying with that perturbation term. And then for this product, as long as all the moments exist, then we still have the odd moments vanishing. But we also have, from the structure that it's written over here, we can swap the integration and the differentiation because of Lebesgue's dominated convergence theorem. We can write the even moments as derivatives of the first moment. And that gives us the ability to write the determinant of moments, the Hankel determinants, as, so we have all of these derivatives of the first moment here, and this is just exactly a Wronskian of this. And so using known expressions in classical books for connections between derivatives of Wronskians and Wronskians themselves, we can then simplify the recurrence coefficients as logarithmic derivatives of just these simplified bn and ans. They are? Yes, yes, exactly. Yeah. So what I then can finally say is that for the generalist higher order Freud weight, now I'm going back to my weight. We've seen that the even moments can be written in terms of derivatives of the first moment, and from the definition we can also write the even moments, again using the integral expression, as just shifted first moments. And that gives us this final simplification that bn, can be written as ant lambda plus 1. And so eventually we get beta 2n just being a logarithmic derivative of the ratio of two ans. And the same for the odd beta 2n plus 1. Okay. So in summary, what we then eventually get for these high order generalized Freud weights, the first moment, we have this integral expression, but this integral can be solved in terms of generalized hypergeometric functions with one numerator parameter. I've written the definition there if anybody is not familiar. So the a sub k's are just the rising factorial, and the hypergeometric function is just a function where for the consecutive terms in this infinite series, the coefficients are rational functions. The ratio of the coefficients are rational functions. So we can express them in terms of 1f m minus 1s like this, and the expressions become even simpler if we add a numerator and a denominator term in the hypergeometric functions. Then we can write them as 2fm's. And they satisfy this ordinary differential equation. So what can we say? Now, I'm going to specify specifically for the case where m is 3, and just show you a little bit of the asymptotics that we were able to derive. And you've seen this before, I think, Anton. But right, so for that weight, the recurrence coefficients satisfy this fourth order nonlinear discrete equation. This is the second member of the discrete Panave hierarchy. And it looks exactly like Freud's, the one Freud got, except here for the perturbation term coming in here. And then they also satisfy the Volterra lattice equation, that the derivative of the recurrence coefficient is equal to this nonlinear product of the recurrence coefficients before and after. This equation, the Langmuir lattice, is satisfied by many more general, not just this weight. So this is a generally known result. And then we can also, from the two above, using a technique by Magnus, get the system of differential equations that are satisfied like this. So from this, we can do some asymptotics. So first of all, the discrete Panave 1 gives us asymptotics as t goes to infinity and negative infinity. So what we see is completely different behavior for even and odd degrees, which is what we expected. So as t goes to, this is t on this axis and beta nt on this axis. So as t goes to positive and negative infinity, the betas tend to 0. In the even case. In the odd case, the betas tend to 0 as t goes to negative infinity, but they go to infinity as t goes to infinity. So there's various things that we can see on these plots, and I have some conjectures for those of you that are interested in open problems. So I just want to make sure I've said everything I want to here. Oh, yes, I wanted to still say that obtaining these asymptotics involve classical techniques. So Laplace's method for t going to infinity, and we used Watson's lemma for t going to negative infinity. So the sketches suggest some interesting conjecture. Oh, I just should give you the recurrence, the asymptotics. So this is formal asymptotics, and those are the expressions. That's what I've shown in the sketches there for different n. So the conjectures I just want to quickly talk about are if beta is odd, then, so that's this case, we see that the recurrence coefficients are monotonically increasing functions of t. And what we also see that the even ones increase. So beta 2n plus 2, say the blue curve, is bigger than the black curve, which is beta 2n, for all t. And these two conjectures are actually linked. Would be interesting to get proofs of them. But the Volterra lattice equation links them exactly. So let me just explain that. So the Volterra lattice equation is linking the derivative to beta 2n plus 1 times the difference between 2n plus 2 minus 2n. And you'll see here that if this is positive, so the derivative is positive, it means that this is positive, and so beta 2n plus 2. So this being an increasing function immediately gives you the second conjecture. So if you could prove one of them, you had both. There's a third conjecture which is fairly immediately obvious from the sketches, and that involves these maximum values. So beta 2n, so the even case has one maximum at t equal to t in 2n star, with every time it's like the leaning tower of Pisa. So t2n star increases as your n increases. And in fact, that is exactly from the Volterra or Langmuir lattice. This is exactly equivalent to looking at where these odd ones cross. So when beta 2n has, so this having a maximum, it means the derivative is equal to 0, which means that beta 2n plus 1 equals beta 2n minus 1. And that's where those cross. Okay. Right. So the recurrence coefficient as n goes to infinity, I was looking now as t goes to positive and negative infinity. This is, sorry guys, this is a classical result. So there's actually not much more to be said, except that we got some additional formal asymptotics. But so this is the Hermite weight, the Freud weight without the perturbation term, right? So Freud had a conjecture that the limit of the ratio of beta n with this n to the 2 over m approaches a constant. And Freud stated the conjecture for orthonormal polynomials, and he proved it for m equal to 2, 4, and 6. And he showed validity whenever this left-hand side limit exists. Then in 1985, Magnus proved the conjecture for m positive and even integers, so for the higher order m's too, and also for q an even degree polynomial with positive leading coefficient. So whenever you have a weight of this form. And then the conjecture was finally settled in 1986 by Lubinsky, Muska, and Schaff as a special case of a much more general result for recurrence coefficients of exponential weights. So a little bit more explicitly what they did is they defined very smooth Freud weights of order 11 alpha with a positive alpha. And the conditions for a very smooth Freud weight, I don't want to go into now because I'm only interested in polynomial powers, and they are satisfied for x to the alpha as long as alpha is positive, and also for polynomial. So with every weight in this class, one can define a number an as the unique positive root of this integral. And so using that for the generalized higher order Freud weight, we get that the beta n's over n to the 1 over m approach this number for each m. So specifically for M3, the generalized sextic Freud weight, we have that it approaches 1 over the cube root of 60, that ratio. Okay, and we can confirm that with formal asymptotics, which we get from the system of differential equations that I showed a few slides ago. So they satisfy the discrete Pandavay second hierarchy equation, and as n goes to infinity, we have the formal asymptotic expansion for n even and n odd And we expect this difference between n even and n odd. And you'll see the leading coefficient is exactly what Freud's conjecture gives you. So in the sketch, what I've done, and this will be interesting when I get to the next case, which is more complicated, where we have this chaotic behavior, but you'll see here we can really predict what happens to the odd betas and the even betas. As n goes to infinity, they are approaching. So this dashed curve is just simply the first two terms of this formal expansion. And the solid terms are more terms of that expansion. And as n goes to infinity, we really are approaching those curves. But there's no chaotic behavior. We can see exactly what happens. Something else that is quite interesting to see, but I didn't put the pictures here, is how dependent on the initial conditions this behavior is. Because if you start with a beta naught and a beta 1, just slightly, like you take 6 zeros away from the correct initial conditions, this immediately goes completely all over the plane. So it's completely chaotic. So the behavior is very dependent on the initial conditions. Right, so finally, I'm now going to the symmetric sextic Freud weight. So just to remind you again, here I'm looking at the quartic power and the quadratic power. So I have two perturbations. The one I'm illustrating the size of the perturbation is with tau and with t, and I'm looking for M3, so the sextic case. And I'm now not giving you the algebraic term, although what I'm talking about I can also do with an algebraic term, but it's more interesting without it. So this is work which was put on the archives a few weeks ago. And we're going to analyze more what is the story with the beta n's having this supposedly chaotic behavior, as the mathematical physicists were saying in the 90s. So the first thing that is very interesting is that, so we have the weight. The first moment is defined like this, and it satisfies this very straightforward linear ordinary differential equation. But we can't solve this guy. The best we can do is to find it as an infinite series of Laguerre polynomials, which basically is an infinite sum of an infinite sum, because Laguerre polynomials are also defined in terms of hypergeometric functions. So we can't say that we have a general closed form expression yet. For the previous weight with just the symmetric, the generalized sextic weight, we could find the sum of hypergeometric, but a finite sum. Here we can't find a finite sum. So although the differential equation suggests that we should find something quite easily, we can't. The best we can do, so even looking at the integral expression, we can't get a general solution. You can try it in Maple, it doesn't give it. And the ordinary differential equation often is a simpler way to get at the solutions. In fact, with the previous cases, it was the differential equation that was satisfied by the moments that gave us the hypergeometric expressions. Here we don't have that. What we do have is for the special case when rho tau is 0, that I showed you previously, we have, so this is M3, so we have a 1F2, and we have a closed form expression. It's a sum of 3 1F2s. And for T0, I didn't show you the detail, but this is so the quartic term plus the sextic term. We can express the moments in terms of 2 F2s, also a sum of 3 2F2s, but beyond that, well, what can we say? This is the question. So what about the moments? If I can't say something general, can I say something about some special cases? And this is what, so we started analyzing the potential. So this sextic polynomial can be factorized as follows. And immediately we notice that there's something going on here. If we can get rid of this term, things are simpler. So it has a double root at x equal to 0, clearly, with the other roots either real or complex, depending on the values of t and tau. And so we're going to just redefine t as minus a quarter tau squared, because that's this critical value. And so we're going to define kappa as minus t over tau squared, and then we can just rewrite this equation like this. So this is just for convenience. And so now we have parameters tau and kappa, not tau and t. And in the three cases below, this potential now in this form, kappa equal to quarter, is immediately obvious to see. You have this factorization of the potential, but also for third and for 0, you get special things happening. And I'll explain a little bit more now from the differential equation why those are special cases. But so it turns out that for those three values of kappa, we can say more. And we get very interesting behavior. So from the differential equation, if I now write that simple differential equation for t and tau, it looks a bit worse when you put kappa, but it gives you the advantage that you can see why kappa equal to 0 and kappa equal to 3, a third, give you special cases, because the differential equation can be solved explicitly in those three cases. And the problem with a third and a 0 is that you have finite singular points everywhere except for those values. So for those three special cases, the first moment, we can write in terms of this sum. It's two Bessel functions, modified Bessel functions, these. They also just, if you don't know these special functions, they're also just of hypergeometric type. So, and then for a third, we get something similar that we get for the case when t is 0, so a sum of two f2s. Now, it's a product of a gamma function with the two f2s, and there's only 3 terms, right? I've written it here with this exponential term just to simplify the expressions. It's just a notation issue. And for kappa equal to 0, you again get the sum of 3 hypergeometric 2f2s. And so there's a lot of hidden structure here, and I'm just going to allude to it here because I don't have time to go into the detail. But if you look at the pattern, a third, 2/3, 2/3, 4/3, 4/3, 5/3. You can always predict what these will be, and even the numerator ones. And here again, that pattern. So third, 2/3. Then the 2/3 comes here. You've got 2/3, 4/3. Then the 4/3 comes here. So you can write them more generally. And for the higher order moments, I'm not going to give the detailed expressions. So they look like the previous page. So there's sum of all the 2f2s in this form, and every time in the numerator you have a plus a third, a plus 2/3, and in the b plus a third, b plus 2/3. So there's a lot of structure, and you can always, guess the. So it's for different a's and b's. You can see the patterns coming through, and the question still is, what about the general case about the moments? But at this stage, we can't say anything more about any other moments. So this is the cases. But there are more interesting cases than just the quarter, third, and 0. So once we have the moments, we'll be able to say something about the recurrence coefficients for those specific moments when kappa equals a quarter, third, and 0. But what can we say about more general kappas? So what we have next is basically numerical results, which we've tried to explain as best as what we can, but it's not analytically proven yet. So if I look at this potential, then I have, there's several cases of interest, and the 3 I'm going to focus on is kappa greater than a quarter, because now I know a quarter is a critical value. So when kappa is a quarter, I have 6 real roots, so double roots at minus a half, so it's a square root of plus minus a half tau, and at 0. Then when kappa is less than a quarter but still positive, I have roots here, here, and a double root there. So it's 4 real roots and a double root at 0. And when kappa is greater than a quarter, then I have 4 non-real roots and just the double root at 0. This is all for tau positive. So I can analyze also for tau negative. So are these the only 3 cases of interest? The answer is no, there are more. So if I look at the evolution with respect to kappa, I'm not going to have time to go into detail in all of them, but we have said more about them. But you get that minus 2/3 is a critical value. I'll show you now why. And then a quarter we've already spoken about, and then we also have 2/5 being a critical value, and I'll also show you why. So what you see, and I'm going to go into more detail with better pictures now, but so kappa less than 2/3, we get this even odd behavior that we saw before. And then as kappa goes greater than minus 2/3, we start getting this chaotic behavior. And then we still have 2 curves, then more chaotic behavior, and then you'll see that the beta n still settle on this asymptotic curve, which we knew. Then they go back for kappa equal to a quarter to settling on 2 curves, but now it's threefold. I'll show you just now in detail. So we have some betas here, and this is actually green and red dots, not just red dots, although you can't see it very well at the resolution of the slide. And then close to a quarter, we still get strange behavior, which is not fully explained yet. And then as we get further away from a quarter, now the initial betas all lie in 1 curve. You notice there's no longer 2 curves. And it's lying in this chaotic region, which is oscillatory to a certain extent, and then they settle on the infinite behavior. And then eventually they settle on this curve, which is just as kappa gets greater, that one goes that way. So let me look at that in more detail. So I'm going to talk, if I talk about this, about the 1 branch case. This is where it starts just with 1. So there, I'm going to talk about this first, kappa greater than a quarter, tau positive. Then I'm going to look at the 2 branch case, so these 2, and then I'll look at kappa equal to a quarter. So I'm looking at those special cases. So to recap, kappa is greater than a quarter and tau is greater than 0. So I know that this potential has 4 complex roots and a double root at x equal to 0. And now taking my this nonlinear discrete equation, if I set beta n equal to beta, so I ignore the dependence on n, then I get this cubic equation. And that's the cubic equation that you would have seen in my sketches up to now. So we can analyze this cubic equation completely, and the chaotic behavior is happening, I'll talk about that now. But basically, the gradient catastrophe happens here when kappa equals 2/5. And that's why 2/5 is also a special critical value of kappa. And that was already discussed in some of the papers in 1990, this gradient catastrophe. Right, so I'm next going to plot numerically the coefficient beta n in the 3-term recurrence for the symmetric sextic weight. The computations were done with Maple. Remember, we don't have the closed form expressions for the betas, but we're going to use the nonlinear 4th order differential equation, this one, and treat it as an initial value problem. So we know what beta minus 1 beta naught looks like. Beta 1 is just the ratio of the second moment over the first moment, but we don't know closed form expressions for the moments, but we'll calculate them numerically using Maple. And then we do the same with beta 2, and from there, those are our initial values. We work with the higher order n's by just taking the initial values into that. But since the discrete equation, this one here, is very sensitive to the initial conditions, it is necessary to use very high numbers of digits in maple, typically, well, usually several hundred digits, but sometimes thousands to do the computations. The earlier calculations in the 1990s did not use an initial value problem. They used a discrete boundary problem for the beta n's to do the sketches that I had on my very first slide. And the thing is that the development of computers and maple during the subsequent years has meant that we are now able to calculate beta n for large values of n through a discrete initial value problem, and we see a lot more of what the behavior of beta n is, but we still have many questions. So first of all, let me just point out, so this is for tau equal to 50. We find that the oscillatory behavior is more pronounced as tau gets larger, which is why I chose a relatively large tau. This curve here is the one that I had on my previous page, which is the beta. I just want to quickly show it. So that's the curve that we get here by setting beta n equal to beta in the Pain-Levé equation. And the first strange thing we notice is that although, because we got this cubic from ignoring n, we expect that as n gets very large, the recurrence coefficients would settle on that curve there, all right? But what's very strange is that for the first initial values of beta, we also get them sitting there. And then we have this oscillatory behavior. We cannot analytically explain exactly where it starts and ends. That's still open questions. And so there's regions where it looks chaotic, then we have the settling down in oscillations. So another interesting way to look at this is by, you see more detail by looking at this two-dimensionally. So this is n on this curve, beta n on that curve. But what about if we look at beta n compared to beta n minus 1? Then we get two-dimensional plots like this. And you can see even better the places where it settles into oscillatory behavior. There it doesn't look oscillatory. And we see that it is tenfold. Here, I think there it's tenfold, there it's sevenfold, then it's fourfold. And initially, the betas follow the curve, and then they go to a point that's the asymptotic behavior. So that's the one branch case. What about the two branch case? So in this case, we have 4 real roots and a double root. Now, because we know that initially there's two values, we don't set beta n equal to a constant. We set beta 2n equal to mu and beta 2n plus 1 equal to v. And we plug it in there and we get this system of equations, which we can sketch like this. We can analyze u and v a little bit more. We know exactly where they turn, and we know that n1 and n2 falls on top of each other here for this value of kappa, which has the solution minus 2/3. So that explains the critical value for minus 2/3. So on the sketches, we'll see that the even betas will follow this curve initially, and that the odds will follow that curve initially. Then as n goes to infinity, they'll follow that beta curve, not the cubic u and v, but the beta curve. And so this is the two branch case. So they follow initially the blue and the red curve, then they have this oscillatory, semi-oscillatory behavior, and then they settle into that. And again, as gamma increases, we see that the region on which this happens, the ends, decreases. To see this now in the two-dimensional version, by subtracting these equations in the UV system, we get this equation, which is just this curve that I've plotted here, the red one. And you'll see initially the betas, they're coming from two sides, then you have the chaotic behavior, then they go to a point as n goes to infinity. And again, here you see the regular regions coming out quite clearly. Here's some more pictures. And what becomes interesting to look at here is as kappa goes towards a quarter, which we know is a critical value, we start seeing threefold behavior. So that's the last case I'm going to have a look at. So when kappa equals a quarter, then the weight looks like this, and we have three double roots. That's where the roots are. And we can solve the moments explicitly in terms of the modified Bessel functions. So already in the 90s, Senator Charles said that the upper branch contains twice as many points as the lower branch. So this is the picture I showed you previously that has beta 3n following this. Beta 3n plus 1 and 3n minus 1, the odd ones, are both lying on this curve. So there's twice as many points on the top curve here. And these are also comprised of green and red dots. So let's see whether we can see a little bit more what's happening there. Now, in this case, we want three. So the threefold behavior, we said beta 3n equal to u and the odd ones equal to v. And do that substitution in this equation gives us a different system of equations. And we can show that u and v satisfy these cubics. And we know that beta itself, if we ignore the n, satisfies a third cubic. So I've sketched all of the cubics here, and analytically they meet at this point, which is given here, so we know that explicitly. And what we'll see is that initially the betas follow this cubic, the black one, which almost lies on top of the blue one. And then the even ones lie at the bottom and the odd ones lie at the top, and then they settle into the beta curve. So just one more thing before I go to the more detailed sketches is that this looks like the blue and the green and the red dots lie on top of each other, but actually they don't. So this is an optical illusion just because we can't see clearly enough. The difference between the U curve, which is at the top there, and the red and the green dots is given by these errors. So numerically there are errors, and it's just an approximation, and we don't know how good an approximation it is either. So lastly, so this is kappa equal to a quarter. That's the best I can do. Now I'm going to just close not more than a minute, I promised, okay. I'm going to look at what happens close to a quarter, because this is not subject of, we've got to write another paper, because we haven't really analyzed this case, but it's very interesting. So what I just want to, I can't remember, I did mention it here. As kappa gets close to a quarter, we see this threefold behavior. And so it's quite complex threefold behavior. So as kappa goes smaller than a quarter to larger than a quarter, you'll see that the blue curve sort of stays constant, but the red and the green swap. And as kappa moves away from a quarter either way, going smaller or larger, you get more oscillations. So moving towards that whole region, either larger than a quarter or smaller than a quarter. But close to a quarter, you see it even better. So we have smaller than a quarter, but there's already the threefold behavior, then it gets more distinct, then it becomes distinct here. And now you'll see the red, and so we know what happens at a quarter. The red and green fall on top of each other, almost. And then they move apart, but they swap position. So it changes to this. And then as it gets larger, then we see that. So numerically, we're seeing very interesting things that we can't necessarily explain yet, all of them. Thank you very much.